additional considerations. Okay? And this is written here. The above equation has both the flux and the head unknown. Therefore, it's necessary to couple this continuity equation with the second equation, which is the momentum equation. And the momentum equation allows us to define, as I said, SS. And the momentum equation can be derived by the Navier-Stokes equation, but let's forget about it, okay? Because this is, when we talk about groundwater flow, actually what we do is to refer to the Darcy's law, which can be derived by the Navier-Stokes equation, but I prefer to say that Darcy's law is just derived by lab experiments by Henry Darcy. In fact, he was the first that through lab experiments defined a relationship between the change in head and the flow in the three directions. So Darcy made, just by lab experiments, he started with a lab experiment in 1D, and then he proved that, of course, the equation could be extended to the 3D domain. What he did was just simply through a pipe, and I will show you a sketch, he measured the relationship between the flow in one direction and the change in head. What he did was, let me show you, there is a sketch of the Darcy experiment. I'm just Googling Darcy experiment, and then I'm looking for images. And let me look for the clearer one. Let me see. Okay, I think this is probably the clearer one. What he did, Darcy, was he set up a pipe and he filled it with sand, with a porous media. And then he poured water through this left pipe, through the porous media. Of course, he put filters here in order the porous media to be kept into this horizontal pipe. And then what he did was, on the other side of the porous media, he measured at a certain level that he fixed, because this second pipe was lower than the first one. The pipe on the right is lower than the pipe on the left. And therefore, given that water is at different levels, he had some water flowing out of the pipe. So he measured the flow that came out from the right pipe depending on the height of the pipe. It's clear that when he lowered the pipe, he got more flow. When he raised the level of the pipe, he got lower flow. And the reason is that what is the level in the pipes? It's the head. As I said, this is our aquifer. When you get on the left-hand side, you get a water level that reaches a certain height. This is the head. On the right side, you have a head that is lower, which means that there is a change in space of head. So he measured the change in space of head, because he knew also the length of the sand, and he tried to relate with an empirical equation the flow to the change in space of the head. It is a very simple lab experiment, and therefore he observed that there is a linear relationship between the change in space of the head and the flow, which is something that we don't a linear relationship between what? Between change in space of energy and flow. It is something that we don't find in surface flow. In surface flow, there is not a linear relationship. There is a quadratic relationship between the flow and the change in head. And the reason is precisely the fact that in groundwater flow, the flow is very slow. a viscous flow. It's not a turbulent flow. In the viscous flow, you may remember from fluid mechanics, there is a linear relationship between the velocity, which means also the discharge of the flow, and change of energy losses. When the flow is laminar, when the flow is very slow, I have a linear relationship between change in energy and flow. This is what he found. And therefore, in mathematical terms, he found this. You see, Q, which is the flow per unit volume, per unit area, sorry, can be written as a constant, as the product of a constant K times change of head in space. Why minus? Because in order to have flow, I have to get a negative change in head. I have to get a decrease in head. And therefore there is the minus. So this is Darcy's equation that allows us to express Q depending on what? Depending on head. Which is precisely what we are looking for. Because if you remember, I said the continuity equation has two unknown, flow and head. But if I can introduce now a second equation which relates flow to head, I reduce the number of variables to 1, which is okay. Questions so far? Oh, there is to say that I was a bit, when I was talking before, I was a bit imprecise because I'm not sure if you noticed that. I said that it was SS that was going to be expressed depending on energy. Instead, it's Q that is expressed as a function of energy losses. Okay, so just because I was a bit. I mixed the two variables. So SS remains unknown for now. For now, yes. Okay. Now what we have to do is simply to substitute this expression of Darcy's law into our groundwater flow equation that we derived before. And that's it. This is what we get. So if you remember, let me go back to the previous version of the equation, the one that we got before substituting Darcy's law, and this is the previous version of the equation. Or let me go to the version without nabla. So this is why we have to substitute Darcy's law. So now we substitute for Qx, Qy, Qz, Darcy's expression, and we get here. We get here. And the minus sign is disappeared because if you remember these terms on the left-hand side were, and if you check on the web page, were negative. Now I can put the Darcy's law in and everything becomes positive. And here now we have only the head that is unknown, which is fine. Remember, we eliminated the flow from this equation. But once the head is defined, if we want to compute the flow, no problem. We have previous expressions for the flow depending on head. There remains here the term SS, which is a property of the aquifer that we have to define depending on, again, on the aquifer's properties. Okay, so let's try to write this equation in a more compact form. We are close to the end of the story, and this is the more compact form. Now I have an nabla squared, because it's a double derivative of h multiplied by k. K is a parameter. It's the parameter of Darcy's law. It depends again on the aquifer. And on the right hand side we have the derivative in time of h, the hydraulic head, multiplied by, again, SS, volumetric specific storage, which is a property of the aquifer. Now, if we refer to a steady flow equation, if we refer to steady flow, we can eliminate the partial derivative with respect to time. So the right hand side becomes 0. And therefore, we obtain the equation that we see here. Nabla square of the hydraulic head is 0. And this equation describes a potential flow. And the potential is given by, this is a Laplace equation, by the way, which describes, if you remember from physics, if you don't remember, don't be concerned. This is something that you don't need to take into account in order to get a conceptual understanding of what we are doing. But in physics, this is a Laplace equation which describes a potential flow. And basically, what is the potential of the flow? It's the hydraulic head. And in a potential flow, the velocity of the flow can be described, it's equal to the, we can describe the velocity by taking the partial derivative of the potential, and the potential in this case is our hydraulic head. Okay. You see here the velocity field can be expressed as the gradient of a scalar, namely the velocity potential. Okay. So this is our equation, and if you look at the concept, and please look at the concept, it's just an equation that we obtain by combining a continuity equation, which is written with respect to a cubic volume, with, we combine the continuity equation with the energy conservation equation, which is given by Darcy's law, which was derived by the lab experiments, which is perfectly fine. I mean, the concept is very easy. And of course, the mathematical development is a bit complicated. What can I ask at the exam? Sometimes, when I see that the student is well prepared, I may ask to derive this expression of this Laplace expression of the groundwater flow equation. And this is typically, I understand, I know that it requires, you know, some degree of memorization, use of memory, and therefore usually I ask this question only when I see that the student is well prepared. Okay. Which is sometimes, you know, it's a bit misleading sometimes, because usually when I make an exam, the teacher realizes from the beginning if the student is well prepared or not. And then if I realize that there are some gaps in their knowledge, then I try to avoid difficult questions. But when we conclude the exam, I may say your mark is 27, and the student doesn't understand because the student says, but I applied to everything, so why do you say 27? And then I try, you know, even when I see that there are some gaps, I try to convince the student. I may ask an additional question, or I may try sometimes to ask the difficult question, not just for the purpose of refining the mark, but for the purpose of convincing the student that there are some gaps. And therefore, you know, anyway, if you wanna really get a very good preparation, I suggest you that just try to learn this development, this mathematical development. If you don't aim to get a laude or a 30, then you can just memorize what are the basic steps, meaning how do you obtain the groundwater flow equation by combining a continuity equation with an energy balance equation, which is given by Darcy's law. And then some students say, I'm sorry, but mathematical development I don't remember. This is fine. I mean, you don't get rejected for this. Okay, I hope it's clear, and if it's not clear, just ask me questions. Okay. Okay, and oh, sorry, I forgot to say one thing about these parameters. K, which is there, up there. What is K? K is called, it's Darcy's parameter. Okay, it's the proportionality parameter between flow and energy loss. It's called hydraulic conductivity. It has the dimension of a velocity. If you make a dimensional analysis, it's a velocity, and it's fundamental behavior, a fundamental parameter of aquifers. So it's a term that you need to memorize, because when you discuss about groundwater, then the term hydraulic conductivity comes out, for sure. So you're going a bump in twin in the future, so I suggest you that you memorize Darcy's parameter, hydraulic conductivity, dimension of a velocity. Okay? And if you don't refer to steady state, then you have also to define for the aquifer the volumetric specific storage, which is another parameter that doesn't really, it's fairly independent by hydraulic conductivity. You don't need to define it if you refer to steady state. Keep in mind that usually when we describe groundwater flow, usually we refer to a sequence of steady states, and the reason is that the flow is very slow. As I said, changes in time are very, very gradual, and therefore the definition of SS is not strictly needed. In classical groundwater theory, we refer to steady state, and the only parameter of the aquifer that we need to know is the hydraulic conductivity. Hydraulic conductivity is necessary. There is no way out from it. And the volumetric specific storage is something that we need when we want to study changes in time, especially when referring to short times. Okay. Now, to solve this equation, we need to integrate it. Okay, the groundwater flow equation is still an integral equation. It's it's an equation of the partial derivatives, and therefore we need to solve it. Okay, to specify the geometry of the control volume. This is something that it's not easy, because you need to specify the geometry of an aquifer, which is something that you cannot observe. So let's suppose that this aquifer also is characterized by different hydraulic conductivities. You may get portions of the aquifer where you have a high hydraulic conductivity. What does it mean? It means that the flow is relatively fast. Hydraulic conductivity, if you look at the Darcy's equation, is what regulates the velocity of the flow. High conductivity means higher velocity. So you may have portions of the aquifer where you have a high hydraulic conductivity, and then as you move in space, you may have zones where the hydraulic conductivity is suddenly reduced. And this heterogeneity needs to be described. Because, again, when I apply Darcy's law in the groundwater flow equation, I refer to a volume of infinitesimal size. But when I integrate, I have to sum over many volumes of infinitesimal size, which can be characterized by different hydraulic conductivities. And therefore you see that the second item that I need to integrate the equation is specify the material properties, including hydraulic conductivity. And then I have to specify initial and boundary conditions, as in any integration problem. I have to specify initial and boundary condition. If I refer to steady state, I just need the boundary conditions. And then I have to solve it by adopting a numerical method, because usually we solve the groundwater flow equation numerically, because the problem is complex, and given the complexity of the geometry, let alone the hydraulic properties, given this complexity, we cannot move forward with an analytical solution. We have to adopt a numerical method. There are several models proposed by the literature. Some of them are available. There is a model that is available open source, which is called, we don't go into the detail of this model, but this is available open source. I never used it, so I wouldn't be able to teach it. And but I am very interested, so I think I try an application in the future, because it's indeed a model that is largely used also by institutional agencies, governmental agencies, by professional engineers. It's not difficult to use. And it's based on the integration of the groundwater flow equation with some possible simplification of the problem. Okay, just to conclude the topic, there is a discussion here on uncertainty. Uncertainty in groundwater models are affected by relevant uncertainty, and like surface models, but in groundwater uncertainty is more relevant. And the problem is mitigated by the fact, as I said, that the flow is very slow. And therefore, if you refer to longer time scales, uncertainty is mitigated, like for surface flow. Because, as I said, describing the short-term variability implies additional uncertainty. In groundwater, we can ignore the short-term variability. We usually refer to larger time scales, like seasons, for instance, and in this case we can reduce uncertainty. The problem becomes simplified. So if you refer to these longer time scales, then it becomes a bit easier to quantify the inputs and outputs boundary conditions of the aquifer, and also the description, the geometry of the aquifer can be simplified, because there are very fine heterogeneity, very fine details in space of the geometry are effective on the short-term changes. If we look at a spatial scale that is larger and a time scale that is larger, then the definition of the details becomes less important. So keep in mind, when you want to describe an aquifer on a large spatial scale and large time scale, the problem becomes relatively simple. But this implies that you describe a large aquifer. Like if you refer to the Emilia-Romagna region, it's an alluvial region. It was originated by deposition of sediments by the Po River, and there is a big aquifer beneath us, which is not so heterogeneous, because, as I said, the region was formed by the same process, deposition of sediments by the Po River. So there are not big heterogeneities, and the region is very large, which means that if I want to describe the behavior of the aquifer at a large scale, here it's possible. But if I want instead to describe a single well, the behavior of a single well, because sometimes even in an aquifer like ours, which is fairly heterogeneous, you may find a single well or a battery of wells that behaves differently with respect to other wells. So there are some wells that are important for water supply, and we see that their level is lower or higher. So if you want to define the single well or battery of wells at the single location and you want to study it, it becomes more complicated because you are reducing the spatial scale, which means that indeed one has to define the behavior of the aquifer at a very fine spatial scale, which is more complicated. But when you enlarge the scales, uncertainty is reduced. But what's important to say is that if in your career you become requested, you get a request to apply a groundwater model in order to estimate the recharge time of a battery of wells or the sustainability of a predefined withdrawal from a battery of wells, the first thing that you have to say to your customer is, look, you are talking about a very complex problem. So it's not like describing the flow of a river, where problem, yes, it's complicated, but it's much easier. So depending on the situation, you may find the opportunity to introduce simplifying assumptions, like enlarge the scales. But in general, as I said, your first reply must be, look, you're talking about a very complex problem. Because today, with the improvement of engineering, with the use of numerical methods, use that has become established just in the last 20 years, there is the convincement by some technicians, by some policymakers, that we have models for everything. And this convincement is also induced by the fact that indeed in meteorology we did fundamental progresses. And in climate science we have people saying that we can predict climate for 100 years ahead, which is, by the way, not true. But the media say that. And therefore, there is the convincement in policymakers that we can have models for everything and we can predict whatever we want. Climate for 100 years, meteorology, which is fine, or water resources for whatever scale. This is not true, and therefore you have to be very clear on that. You have to gain a knowledge of what's possible and what's not possible. And I'm trying to help you, but of course you have to integrate this information. So the first thing that you have to think is whether they are asking you something that is possible. And when you don't have a long experience, this is not an easy assessment that you have to make, because especially if you take a low profile, which I highly recommend, you are tempted to think that if a technician or a policymaker asks you for something, then it must be possible, otherwise they wouldn't ask you. This is the reasoning that I make usually, like, okay, they are asking me something that I don't know whether it's possible or not, but if they are asking, probably that's possible. This is not actually what happens. Sometimes policymakers ask for something that it's not possible. So what I suggest in building your experience is, first you have to try to understand what's possible, what's not possible, under what condition an application of something that in general is not possible may become possible. And you know, this, especially when we talk about groundwater, my suggestion is be careful and try to make clear that we are talking about something that we cannot see, that we cannot easily measure. We are talking about a media, a porous media, that cannot be easily characterized. It's not like a river where you send a surveyor to take the geometry of the river and the surveyor gives you back a survey of the river cross-section. It's not like that. In this case, you have to send out people digging wells and making experiments on wells. It's not easy. So, you know, when we talk about groundwater, as I said, it's something that is really delicate. Okay, now, groundwater for me, it's here. You see just a couple of hours of lectures. But we are done also with the big chapter of deductive methods for water resources assessment. So we talked about inductive methods, and they said measurements of water level in wells and river flow in rivers. Inductive method. deductive methods, models, that try to reproduce the dynamics of river flows and groundwater flow. And now we are ready to move forward. Ready to move forward means, first of all, given that we talked about models and we talked about parameters, let me dedicate a relatively limited amount of time in explaining to you how parameters are defined. So in this case, there is K to define, there is volumetric specific storage to define. In the case of IMOD, there is beta, there is alpha, there is Cmax, and then Ks, Kq to be defined. How do we define these parameters? This is a typical problem of engineering, which is also a bit nice to be studied, because it's not difficult and it's something that we can easily understand. We have these numbers, I define parameters. They are typically constant values in the body of a model that typically characterize the properties of the control volume. It can be the catchment, it can be an aquifer. They are introduced in order to give flexibility to the model, to be applied to different catchment, different aquifers, but they need to be estimated. And in fact, when I applied IMOD, I told you, if you remember, at the end of the exercise, we tried to change the parameter to find reasonable values. This is a way of estimating the parameters. What I did last time, at the end of the exercise, was a trial and error procedure. I had an observed hydrograph, I had a simulated hydrograph from IMOD. I changed the parameter until I found something that looked not bad. This is the trial and error procedure, which with the use of the computer is very easy. But let me now refer to a specific web page, model calibration and validation. We will see what they are. Okay, so here you see calibration through optimization of model performances. First of all, let me clarify what the meaning of the term. Calibration means identification of the best value of parameters. There are several synonyms for calibration. The most used probably is parametrization. Parametrization of a model. Calibration of a model. Sometimes people say optimization of a model or optimization of parameters. Calibration is the most widely used term, and the most frequently used calibration procedure is by comparing observed and simulated data. This is what we did at the end of our exercise. Typically, when we talk about surface flows, we have an observed hydrograph. You see Q observed, the continuous line, and we have simulated data, the points. We change the PC parameter values until we find the best possible simulation. The same can be done for aquifers. You have observation of water level. You have observation of rainfall, which means recharge, which means Q in an aquifer. You put rainfall into mod flow, and then you get simulated water levels into wells, and then you compare simulated versus observed. When we use this procedure, there is a big advantage that we look at it, we look at the result. And it's an approach that an engineer likes a lot, because you look at, you have a look, and you judge by visual if a result is reasonable or not. You assess by visual assessment uncertainty. Because of course, by looking at the difference between observed and simulated hydrograph in this case, you get an assessment of uncertainty. Okay, This is a trial and error procedure. What is the downside of this procedure? It could be long, could be very long, and because you know, in class we had a model that performed the simulation very quickly. iMode is a very quick model, but there are models that take time, and therefore if the simulation takes a longer time, and you have to wait 5 minutes before displaying the hydrograph. You quickly understand 5 minutes is still a reduced time, but you quickly understand that you cannot wait 5 minutes. If you have to make like 50 attempts, you cannot wait 5 minutes. It becomes very quickly impossible. Also, you don't know whether there is a better combination. There could be. When you have 5 parameters like in iMode, you get to a situation where you could say, okay, it's fine to me, but there might be another better combination of parameters, and you don't know if there is another better combination. So this procedure works well when you have a clear object, like I'm just interested in the peak flow, and therefore it's very easy for you to see at a certain point, like here, if the peak flow is fine. And you know that for your purpose, technical purpose, if you make an error of 10% on the peak flow is perfectly fine. So when you get a simulation like this one, you say, I don't care if there is a better combination that gives to me a 1% improvement. I am just fine. So when the objective is clear, and when the model runs relatively fast, then trial and error is fine. Because, as I said, it gives to you the advantage that you clearly see what's going on. And also, by doing the trial and error procedure, you learn what is the effect of changing one parameter with respect to another. And this is something very useful because you get to know the model much, much better. You understand what are the parameters